Okay, good evening everyone. In this lecture, we are going to discuss about fluidized catalytic cracking unit. Okay, so fluidized catalytic cracking unit is one of the most important unit in any refinery configuration, and here is a typical refinery configuration. If you see here, here in last video, last lecture, basically we discussed about vacuum distillation unit, and during our discussion, we explain that the side product of vacuum distillation unit is usually a feed of fluidized catalytic cracking unit. So here you can see the feed of FCC unit is taking from the side product of vacuum distillation unit like light oil, intermediate oil, heavy oil, and these are the side product which is the feed of FCC unit. At the same time, if fluidized catalytic cracking unit is say resid fluidized catalytic cracking, in that case even vacuum residue, that is also called salt residue, this salt residue can also be a feedstock of fluidized catalytic cracking unit. So we have, if you look at this, so we have feedstock coming from vacuum distillation unit, side product as well as bottom product. Okay, apart from this, if there is a furfural extraction unit, then extract can also be sent into FCC unit. And here you see this hydrocracker unit bottom product, the hydrocracker unit bottom product, that is also called UCO, unconverted oil. This is also a feedstock of FCC. So if you look at this refinery configuration, then in that case we can say that the feedstock of FCC is vacuum gas oil. Basically it comes from vacuum distillation unit, and then the bottom product SR can also be feedstock depending on the whether it is FCC or RFCC. If it is RFCC, then SR can also be a feedstock. Apart from this hydrocracker bottom product, which is also called UCO, unconverted oil, that can also be a feedstock of FCC unit. If there is a unit like furfural extraction unit, then extract. Similar way, if there is a propane defaulting unit, then defaulted oil can also be fed into FCC unit. Similarly, slack wax can also be fed as so there are several streams which can be act as a feedstock of FCC unit. And what we are getting from FCC unit, we are getting products like dry gas, which is also called fuel gas, and then LPG, LCN, which is again treated in MSQ, motor spirit quality upgradation unit, and basically it is based with we basically make petrol, or we call it gasoline. And then TCO, which is a combination of heavy cracked naphtha plus LCO. This is usually treated in hydro treated reactors like DHDS or DHDT. And this bottom product is called DCO, that is again fed into this DCO, delayed coker unit. So we are getting products like fuel gas, LPG, LCN. Based on that we can make it petrol, and based on TCO we can make it diesel. So these are the products we are getting. So how we are getting it, we will discuss here in this. Now about feedstock or throughput of FCC unit. Generally 10% of crude throughput is the throughput of FCC unit. When suppose our crude distillation unit having capacity of 1000 kg per hour or 1000 tons per hour, then FCC feed capacity will be around 100 tons per hour. So is based on the refinery configuration, it may vary, but it is a rough estimate. Anyway, now before I delve into how this we are achieving, let us understand the importance of this FCC unit. The FCC unit is one of the most important unit in refinery, and one of the most complicated also. And if you learn FCC unit thoroughly, then many people say that around 40% of refinery knowledge you can gain just by knowing FCC unit. This is one of the most critical and as well as most complicated unit in refinery. And many people say that if you are a chemical engineer and if you have a working experience of FCC unit, then you have learned almost every type of equipment and as well as processes. So FCC unit is very important for even learning point of view. But right now here I am explaining about why it is very important in refinery. This is very important because it's called as a gasoline machine. So refinery 40 to 60% of gasoline production comes from FCC units. So the most important product, one of our most important product is petrol, and that is mostly made in FCC unit. And FCC unit is why it is very important, because it is converting very low value feedstock, like as you see, have gone we gone through the feedstock, like vacuum gas oil or short residue. This type of feedstock is converted into very high value products like LPG and petrol or diesel. So this is very important. It's a profit making unit in any refinery. And apart from this, this FCC unit can be designed in such a fashion, then based on our design, based on our requirement, it can be run in different mode. Like if your diesel requirement is very high, then based on catalyst or based on catalyst oil circulation ratio, we can make our main product as LCO. Similarly, if petrol production is required, then we can change our catalyst oil circulation and catalyst, and this is then FCC unit will be for gasoline production. I mean, it can be operated in different way. Even LPG production is required very high. In that case also, we can change our some operating parameter and catalyst, and then based on that, LPG production will also go high. So whatever your requirement, FCC can fulfill it. Even the petrochemical, which is very high, even you when we are going to say uh, electric vehicle, in that case also FCC will remain important, because FCC can produce LPG at very high amount, and from there we can separate propylene and ethylene like thing, and that these are the feedstock of petrochemicals. So in any case, FCC will be important. FCC is important, and FCC will remain important in refinery configuration. So we have several parameters. By changing these parameters like riser outlet temperature, catalyst to oil ratio, catalyst type, we can make our one product to other depending on our economics. Okay, anyway, so let us start our discussion and see this unit is what is the full form of this unit. Okay, so the full form of this unit is, it's a cracking unit, and this is catalytic cracking unit. Okay, so reaction is catalytic reaction, and what it is doing is cracking of very large molecule into lighter molecule. And where it is cracking in a fluidized bed reactor. So the name itself suggests many things. It's a fluidized catalytic cracking unit, means cracking is taking place in the presence of catalyst and in the fluidized bed reactor. So okay, so this is a catalytic cracking reaction, so there must be some catalyst. And what is this catalyst? See, if you are learning about the secondary processes like FCC, hydrocracker, or all those things, the delayed coker unit and whisper, these type of DHDS, DHDT, these type of units can be better understand by first understanding the what is the catalyst and what type of reaction is taking place. Because if you know the chemistry, then you can even predict how the equipments will be. So let us first learn about the catalyst and reaction, how what is the catalyst and how it acts, as well as what type of reaction is taking place, and then we'll go into the processes. Okay, so FCC catalyst is basically made of four major components. The one is that the primary major component is called zeolite. That is the main active ingredient of catalyst. And apart from zeolite, there will be matrix. That is also having some important purposes. I will discuss about. Then clay, and all these three will be bind by some another component that is called binders. So with binder, we are basically binding zeolite, active matrix, and clay. And these are very porous catalysts and very fine particles. Like if you have seen sand, it's look like this sand type of particles. Okay, and having very high surface area, and particle size is may vary from 10 to 150 microns. It's a very small type of particles, and it's look like a white sand. Okay. uh, Okay, so let us first learn about what is zeolite. So this is again a typical representation of FCC catalyst, which is made up of zeolite. There could be different type of zeolite, and apart from this, there would be matrix, there will be clay, there will be binder, and apart from this main catalyst, we can also add some additives to change our reaction based on our requirement. Suppose our requirement is LPG production should be high, then if we add some additives in the main catalyst. So we will discuss about it. So let's first discuss about zeolite. What is zeolite? Zeolite, you may have heard about the molecular sieve. It's a very important catalyst. Uh, and this is a very vast subject. Several books has been written only on this catalyst, so I cannot delve into much detail, but a very basic understanding will be provided in this lecture. And what is this zeolite? Zeolite is basically crystalline aluminous silica. Now look at this structure. This is a basically tetrahedra, and at the center of this tetrahedra there is a silicon, and there is another aluminum. So one aluminum is connected with four oxygens, and generally we know that aluminum remains in +3 oxidation state. So there will be a net negative charge on aluminum, while silicon will be neutralized because it's having +4 oxidation state and connected to four oxygens. So there won't be any positive or negative charge net. However, on aluminum there will be net negative charge, and to neutralize this there is a H plus ion. So if this type of zeolite, this is called HY zeolite catalyst. There could be several other type of zeolite, like if it is neutralized with sodium then it is called NaY, and there could be several other way. If it is neutralized with some rare earth then it is REY, called, it's like that. Now, because of this H plus ion, this zeolite act as a Bronsted acid. Now, see, I am explaining how catalytic activity arises with zeolite. See, uh, this negative charge is neutralized with this H plus ion, and this H plus ion act as a acid. So this will act as a Bronsted acid. One thing. Another thing is, at very high temperature what happens, these two H plus and one oxygen will separate at high temperature, and because of this separation there will be plus charge on this silica, and then it will act as a Lewis acid. So this zeolite can act as a Bronsted acid as well as Lewis acid at very high temperature. So this is again here represented as zeolite at very high temperature. It H2O can be liberated, and this will become an active Lewis acid site because it will accept electron. Okay, so why I'm explaining that this zeolite can be acted as a H plus site, or sorry, a Bronsted acid or Lewis acid site, because this is the reason why abscisic reaction is taking place with this zeolite. Let me explain you. See, this can act as a Bronsted acid site, means this can donate protons. Okay, and this can act as a Lewis acid site. It means it can accept electron. This is a very simple chemistry we have learned in our school also. So suppose one olefin is there, and if it is acting as a Bronsted acid site, so it will provide H plus ion, and then this carbocation will form. Okay, similarly if there is a alkane, and if it is acting as a Lewis acid site, then it will basically H minus ion will be accepted by this Lewis acid site. So then again carbocation will form. So due to this zeolite catalyst, due to this acidity of this zeolite, olefins or alkane may convert it into carbocation, and once carbocation will form, there could be several different reaction will taking place, because we know that tertiary carbocation is very stable. So this carbocation will rearrange and will try to form into tertiary carbocation, so isomerization reaction will take place. So in FCC, isomerization reaction will take place. One reaction we have understand based on this catalytic properties. Okay, another reaction. See, this carbocation, this bond is called alpha bond, this second bond is called beta bond. Now wherever there is a positive charge, now beta bond is usually very weak bond. So this beta bond can be breaked because of this. We have learned in school about this in basic chemistry. So this bond can break, and if this bond break at this side, then this will form R plus ion, and one olefin will form. And if this beta bond will break, then what will happen? R dash CH2, and then olefin will form. So you see what is happening here. A big large long chain molecule is breaking or basically cracking into a small molecules, and olefins are forming. So you see here, because of this zeolite, two different type of reaction we have explained right now. The one is cracking reaction, and based on cracking reaction, large molecules is cracking into smaller molecules. At the same time, olefins is forming mainly, and as well as due to this carbocation rearrangement, isomerization reaction is also taking place. 1 minute. So I hope the up to this point everything is clear, and now let us understand some other type of reaction which might take in FCC. So because there is it's a complex series of reaction is taking place in FCC, and almost every reaction, cracking reaction is basically endothermic. So it is the main reaction. FCC reaction is mainly endothermic. So apart from this cracking and isomerization, there is another type of reaction that is very important, that is called hydrogen transfer reaction. And hydrogen transfer reaction, how it is taking place? Here two olefin molecules, or one olefin or one naphthalene. So one in this reaction, one reactant will be olefin, that is for sure, and another reactant could also be olefin, or another reactant could be naphthenes. So these two react and hydrogen transfer taking place, and because of this, one olefin will be converted into paraffin and another is converted into aromatic react. Similarly, here one is paraffin and another is aromatics. So this is another type of reaction that is taking place, hydrogen transfer reaction. Apart from this, there could be dehydrogenation reaction because of these metals which is coming from the feed, and this may also promote dehydrogenation reaction. And these are the some desirable reaction, hydrogen transfer and cracking or isomerization, while dehydrogenation reaction is undesirable reaction. We will talk about this later on. And apart from this, there is another reaction, that is coke formation reaction, and it basically what it happens, unsaturated I means olefins or multi-ring aromatics basically polymerize at these conditions and forms coke. It's a polymerization and condensation reaction. It's a complicated mechanism, so we'll not delve into the. So basically what are the reactant for coking? Unsaturated, I mean olefins or multi-ring aromatics may lead to form coke formation. So these are the reaction which is taking place, and how it is taking place I have explained. Apart from zeolite, there could be matrix, and this matrix, what is the purpose of this matrix? Basically zeolite zeolite is having very small pores, and because of that there is a selectivity in zeolite, so everything cannot enter into zeolite pore. Okay, so how will you convert the very large molecule means crack very large molecules, because large molecules cannot enter into zeolite. So there is another active ingredient in catalyst, that is called matrix, which basically crack a larger molecule into some smaller molecules, and then it will go into zeolite, and where it is selectively cracked into petrol or diesel, LPG company. So basically it enables FCC catalyst to process heavier feedstock with large hydrocarbon molecules. And out of apart from this, there would be binder, which will basically provide physical integrity of and mechanical strength of FCC catalyst. So these are the FCC, this is all about FCC catalyst, and during this discussion I have also discussed about type of reaction which is taking place in FCC catalyst. Okay, now let us learn about some deactivation mechanism of catalyst, and this is a very general understanding. It is a basic in chemical reaction engineering, and these basic understanding will also be useful in this FCC discussion. So I have just summarized the deactivation mechanism. There could be several possible way to deactivate a catalyst, and some are temporary deactivation while other are permanent deactivation. So one temporary deactivation is coke formation. So coke, I have already explained that coke will also form during this reaction, and this coke, what it does, it adsorb on this active site of zeolite, and because of this catalyst will deactivate. So its catalyst deactivation results from a coke material deposition on surface of catalyst. This is basically temporary deactivation because it's a reversible, means if you burn the coke, active site will again free. So this is a temporary deactivation. Now apart from this coking, there could be other deactivation called sintering or aging. This happen at very high temperature. See, at very high temperature, now what happens, this porous structure will destroy, and because of this porous structure will destroy, catalyst I mean reactant cannot enter into this pore, and the reaction will not take place, and this happens at very high temperature of gaseous temperature. So this will permanently deactivate the catalyst. Another thing is third type of deactivation is also called poisoning. Here what happens on catalyst active sites, this some metals adsorb, and that is adsorb chemisorb, matlab chemical adsorption will take place, and this type of adsorption is the irreversible adsorption. So once it has been adsorbed on the active site of catalyst, it won't be available for our main reactor, and so in that way catalyst will deactivate permanently. So catalyst deactivation, all three type of deactivation may take place in FCC, and we will discuss while we discuss the uh, reactions. Okay, so we have discussed about the catalyst, we have discussed about the reaction, we have discussed about the catalyst deactivation process. Now we will discuss about the process. So before I go into the process flow diagram, let us first understand what is fluidization, because this reactor is basically fluidized bed reactor, and if you have gone through this fluidization, so it will be very easy for you to understand. But anyway, I am explaining very briefly what is fluidization here is, uh, uh, and then we will delve into the process. See, suppose we have a fixed bed of catalyst here. Fixed bed of catalyst means catalyst particle is there, and in that case, suppose if there is a catalyst particle on this column, and if I am providing gas from the bottom, then what will happen? Basically, I am drawing here. Suppose these are the catalyst particles. So what will happens? Gas will move from this catalyst particle like this, and this intrapore structure is uh, intraparticle spaces. From these path, gas will flow. Okay, and this type of reaction will take place in this type of reactor is called fixed bed reactor. So basically, gas is moving through the catalyst, the intermolecular uh, gap. Through this intermolecular gap, gas will move, and during this reaction, would means fixed bed reactor in fluid particle move like this. Now suppose I'm increasing the gas velocity. So what will happen? If you increase the gas velocity, the drag force on the particles will increase. So see, there is if there is a catalyst particles, so what are the forces acting on this? One is gravitational force due to its weight, and another is the drag force, which will try to move in upward direction. So when we increase the gas velocity, if you are increasing the gas velocity, what will happen? It will, at one point, this fluid particle will lifted, I mean its weight will be lifted by the drag forces, and that becomes the fluidized bed, and that velocity is called minimum fluidization velocity. You have might have learnt about in your college. So that is the minimum fluidization velocity. So this could be this bed. Now here catalyst has been just lifted, but that catalyst is right now homogeneously, means at every place catalyst density is more or less same. Now if you increase further gas velocity, now what will happen? There will be heterogeneous mixture, means at some places there will be very less catalyst, that is called bubble. So the bed will be now bubbling bed. So and on another places catalyst density will be very high. There could be another uh, zone that is called slug flow, where almost one cross section there is no catalyst, another cross section very high catalyst. Now if you increase velocity, if you keep increasing velocity, then there could be turbulent, means everywhere it's a turbulent zone. And if you further increase the gas velocity, then whole bed will not will start moving with the gas, and these will act as if like this catalyst particle will this will act like a fluid. So see, why I'm explaining is this is fluidized bed reactor. This catalyst particle which is solid, because of this fluidization, it will act like a fluid which is moving from the lower bottom to upper side. Okay, and it's just not act like this. It is basically I mean even mathematical relationship will work. Every fluid mathematical relationship will work, like you can apply P plus rho gh and everything. Bernoulli equation you can apply here. It's like that. So this happen at very high velocity. When you increase the gas velocity sufficiently high, then it will pneumatically convey the fluid particles. And these all fluidization regime na, you will observe in the FCC different section. I will discuss about it. So here you should understand that this, because of this gas velocity, I am converting this solid particles as a fluid, and there we will apply every fluid mechanics formula. Okay, now here I am explaining the process, and this is the heart of FCC, that is called reactor regenerator section. So basically I have explained FCC in very detail on my YouTube channel. I've just taken a screenshot from here, and here as I explained in the last part I explained that any feed which go into any unit, it first come to surge drum. And I explained that there are several reasons of surge drum. One is that if our ominous pump disturb, then also our unit will not disturb because of the surge drum, because it will provide residence time. At the same time, if water is coming from the feed, then there is a boot in surge drum, and that can be separated, and in that way our unit won't disturb because of this water. Otherwise, if water is coming now, this water can create a lot hell of problem, and many time unit get disturbed, even unit trip due to this water. Its water suppression is very high because water vaporizes and it's create a very large volume. Reactor pressure suddenly increases very high. So I will discuss about this. So right now, suppose whatever the feed is coming is will first come into the surge drum, uh, and from surge drum there is a feed pump, and it will go through a series of heat exchanger network. Okay, just 1 minute. So as I explained in the last lecture, in any unit, feed will first go into heat exchanger network, where feed will be heated, and at the same time product will be cooled. So here in FCC also feed will be heated, and the same way in last lecture video unit, first it will be heated at the top product, and then bottom product is like that, and finally to go to furnace. And here generally we heat our feed up to say 240 degree, 50 degree, 260 degree, depending on the requirement. We change that coil outlet temperature of furnace. Anyway, after this heating now, this go into this riser section, and this is the main reactor. So here is a misnomer, because this is basically, this is called reactor and this is called riser. Our main reaction will take place in the riser, and this reactor is just for separation of catalyst and the product vapor, but it's tradition to call it reactor, and this is called it riser. So riser is basically a very a long standpipe, and it's a hollow standpipe. There is nothing inside this, and their catalyst will circulate from regenerator to this riser, and then reactor, then again regenerator, and this type of circulation will take place. I will explain how. So basically the feed which is coming at through the furnace will feed into this riser, lower part of the riser. And here you will see this, there is a is sorry, okay, let me explain. Okay, here you will see this is the nozzle of the riser, here where, sorry, okay, here you can see it, this here feed oil means preheated feed will enter, and here MP steam will be provided. And when it goes through this nozzle now, this what will do it, this MP steam will break this feed into very small particle. And why it will break it, it will, in that way it will increase the surface area of the oil, and when surface area will increase, heat transfer will take place, and it will enhance vaporization. And why I'm explaining this, why vaporization is required, because the reaction which will taking place in this riser should be done in vapor phase. Why? Because catalyst particle is very small particles, it's like sand, and suppose there is a sand, and if you provide liquid, then mud will form. Okay, there should not be liquid in this whole process. The feed which is coming the liquid phase should convert into gases as soon as possible, and for that there is a nozzle, and that basically break the feed into small particles, and there a hot regenerated catalyst is coming, and hot regenerated catalyst will be in contact with the feed, and it will vaporize the feed immediately, and then this gas, I mean feed gas and catalyst, hot catalyst will move into the upward section, and when it move in the upper section, because this is a pneumatic conveying zone of fluidization, and when it moves in upper section, during this movement reaction will take place, and this type of reaction is basically endothermic reaction, as I have explained. So during this movement reaction will take place, and during this reaction our product will form, as well as coke will also form, and coke will deposit on the surfaces of catalyst. So catalyst will deactivate, and at the same time product vapor will form. So once this reaction will take place now, then our main purpose will to separate this catalyst, so that I will burn this coke, and catalyst will again regenerated, again become active. So I have to separate this catalyst with product vapor, because product vapor is our main aim, that for that we are doing all these processes. So we have to take out the product, and we have to separate product vapor with catalyst, so that catalyst can be regenerated and product will be separated in different different distillation range like LPG, LCN. For that there is a product recovery section. There will be a main fractionator column, and there will be gas section. So I will not discuss a detail, because that will take a lot much time. Apart from this fresh feed, there could be recycle also, like there is a SCO recycle, slurry recycle, and all these nozzles, there is MP stream provision to uh, break the whatever the recycle we have. Apart from this, there could be other breeze breaker unit, naphtha can also be taken here in the riser. So there could be several nozzle during at different height of this riser, and riser is very high, means very long pipe, and during this reaction take place at very high, means this gas velocity will remain very high, so that this whole riser will be traveled by gas in only 2 to 3 seconds. Only 2 to 3 seconds. Otherwise, if you provide much high residence time, then undesired reaction will take place. So only desired reaction should take place, and so that this gas velocity will remain so high that this much height of riser, say 30 meter of height riser, will be traveled within 1 or 2 seconds. And once it has been traveled, reaction has been taken place. Now our aim is to separate catalyst particle with product vapor as much as soon as possible. Why? Because catalyst will remain in contact of product vapor, then product will be converted into the unwanted product, like fuel gas is our unwanted product, it's not our desired product. So LPG will further crack to fuel gas, petrol will further crack to LPG, it's like that. So we should not allow our product vapor to remain in contact at very much, very large duration. So what we do is, when the riser, uh, where riser end up, there is a riser termination device. Okay, this is riser termination device. Riser termination device could be of different type in different units. I am explaining here about how it works. It's a kind of 3D arrangement, and it is very difficult to explain. If whether I'm visible or not, I will try to explain. Basically, riser where it ends now, there it is. It's a kind of roof here is. So whatever catalyst particle is going now, it will collide the roof, and catalyst particle will move in downward direction. Okay, and during this downward direction, there is another pipe. I will very difficult to you may search about Ram's horn separator, how it works. So during this downward movement, there is a gas pipe, and through this gas pipe na, this product vapor will move in upward direction. So this is our initial separation. With this riser termination device, catalyst particle will move into downward direction and gas particle will move in upward direction. So of course this is not a perfect separation. So with gas particles, some catalyst particle will also move in upward direction, as well as with catalyst particles some gas or product vapor will also move in downward direction. So further separation is required. This one was initial separation, that is called riser termination device. Okay, now the gas which is product gas which is moving in upward direction with uh, it might be possible some catalyst particle is also has been carried out, and to remove that catalyst particle there is a cyclone separator. Okay, cyclone separator, how it look like, I will show you. These are the cyclone separator. Okay, uh, it's like a, a, a series of cyclones will be there. Basically what it happens in cyclone separator, uh, cyclone separator, the gas will basically, if there is a cyclone, it's like that, gas will enter tangentially, and when it enters into the cycle now, due to this entrance, gas will follow a circular path, and during this circular path now, catalyst particle which is heavy, having high density, will move towards the outer periphery, and the gas will remain in the center, and the gas will ultimately move out from the cyclone from the top, and catalyst particle which is go into the outer periphery, ultimately move into the downward direction, and from there catalyst particle will move go into bottom, while gas move at the top. It will work like this. So whatever the gas is, the product vapor is taking going, it will move into the set of cyclone. It might be possible there will be primary cyclone, then again exit of it will go into secondary cyclone. It's like that, and the catalyst will move in downward. So catalyst which was going downward from the riser termination device as well as from cyclone will move into downward section. And of course the catalyst which was coming from the riser termination device will also having some product vapor, and that we need to separate. Why we need to separate? Because that product is our main purpose. So we would not like to expense the product vapor into the regenerator, because there regenerator in regenerator our product will be burned, and that is or not our desirable thing to do, because we are doing all those things for just our product vapor. Apart from this, there are several other issues, because it's like we are feeding petrol LPG into the regenerator, we are providing air, and we are just burning our petrol LPG. And during this because of this high uh, calorific product, if product will go into the regenerator temperature will go very high, and it will even create a metallurgical issue. So it should not go, and there could be many other issue. I will not go into very detail. So to avoid this, we need to separate our product vapor. Okay, and for that there is a stripper. So basically the whatever the catalyst which was coming from this riser termination device will go to the stripper, and where we provide main stripping stream. So there are two type of stripping stream there. One is called pre-stripping stream, means once the catalyst particle move in, it will first strip down, just pre-stripping, means whatever it could do, just separate the gases. And then there is a stripper. I mean there will be tray, and with this stripper there will be, with main stripping stream, whatever the product vapor can be will be separated, and it will go into the upward section, and ultimately it will move from the reactor in the top. Okay, and the catalyst which is now free of product gases will move from this standpipe to regenerator. Okay, now catalyst there is a coke, and so we need to burn it. And to how we are going to burn it, we burn it by air. So we have a blower that is called main air blower, and with main air blower we will provide air to this regenerator. So in regenerator we will provide air, and the catalyst, a spent catalyst will move into the regenerator, and there will be reaction will take place, and coke will burn into CO or CO2. Okay, so I will discuss about this, but before I will discuss about this mechanical arrangement, how it is arranging here. uh, let me, okay, there is less time, but anyway I will explain it. Here this is a large diameter vessel, okay. So catalysts need to disperse homogeneously, otherwise what will happen, if this is a cylinder and catalyst is just drop out, then what will happen, at one side there will be uh, catalyst height will be very high, at another side catalyst height will be very low, and if I provide air, then what will happen, here air will be remain unused, while here air will be, whatever the air is going will be consumed much, and this catalyst coke will I mean could not burn. And what will happen, there will be CO formation because of less amount of air, and this CO when at higher elevation will be contacted with this unused air, and there will be CO2 formation. At higher elevation there is no catalyst to absorb this heat, and because of this temperature will go very high at the upper section of this regenerator. This is called afterburning. That's a very undesirable phenomenon. So to avoid this afterburning, the catalyst will be dispersed homogeneously, and for that there is a bathtub. So this is again another distributor of a spent catalyst. Similarly, air should be distributed. For that, there is a ring that is called air ring, and there is a outer air ring and inner air ring. It's just like a ring, and that ring there is a small hole through which air will go into the whole periphery of this regenerator. Okay, now this spent catalyst will then contact will be in contact with air, and the coke will burn, and during this reaction shocks shocks will form, and apart from that CO will form, CO2 will form, on unused nitrogen and oxygen will be there. These are called flue gases. So flue gas will form, and again as I explained here, here will be also the flue gas will, when it move upward direction, it will take some catalyst also, and so to separate catalyst from the flue gas there will be cyclone separator. So here in regenerator also there will be cyclone separator, okay. Now I will explain some other thing here, but before that one very important thing in FCC is need to be explained here. See, this is a very critical unit. Why it is very critical unit? Because in refinery we usually deal with hydrocarbon, and we generally try to avoid contact of hydrocarbon with air. But here what we are doing is, there is a regenerator where we are giving air, at the same time there is a riser reactor where we are giving hydrocarbon, and we are just means avoid contacting with hydrocarbon with air with the help of this slide valve. This is a spent catalyst slide valve, this is regenerated catalyst slide valve. So it is very imperative to maintain healthy differential pressure with this slide valve, because uh, catalyst is moving from this reactor to this regenerator, and suppose this pressure differential goes negative at this juncture, then what will happen, air will move in the opposite direction, and due to this air there will be explosion, because here is a hydrocarbon and air is mixing with this, then it will a very big blunder. Similarly, this regenerated catalyst is moving into the riser through this RCSB valve, and if this delta P goes negative, then hydrocarbon will go into the regenerator where we are providing air. Then hydrocarbon will burn, and this is again a flow reversal. We call it flow reversal, and it will be a disaster. So this need not to be happen. Okay, and now suppose you will ask why it is not happening that. Feed, I mean hydrocarbon is not going into this regenerator, why only this catalyst is going. This can be explained because of this sealing in reactor due to catalyst level. Why? Suppose there is a liquid in a cylinder, and uh, in the upper section there is a gas, okay, and if you are taking out the liquid now, so gas will not go out till that there is a level in this cylinder, because of this liquid there is a sealing, and it will not allow gas to move into the downward section. So similarly here, this is happening. There is a catalyst level in the reactor, and it won't allow gas to move into this section, because it will act as a fluid. Now I have explained that the catalyst will act as a fluid. uh, so anyway, so this SCSB, this is spent catalyst slide valve, is controlled by the level of this reactor. So when level goes high, then SCSB will go, opening will go high, and if level go low, then SCSB go opening go low. Okay, now at the same time, the SCSB opening will also be decided by the DP across this slide valve. Why? Because this DP is very critical, because DP we need to maintain positive all the time, and because of that, there is a override controller. Override controller means this slide valve will act based on this level till that this DP is healthy, and if DP is getting low, I mean, say limit is given of 0.1 kg per centimeter square of DP, then if DP is going low, in that case it will forget about the level. It will just act based on this DP and will start closing this slide valve, and in that way it will avoid the flow reversal. Anyway, there are several different type of regenerator, and we will not go into the detail because the limitation of time. There could be full combustion regenerator, there could be partial combustion regenerator, there could be two-stage regenerator, as I have shown here, depending on the different type of FCC unit. Whatever type of FCC unit, if there is a full combustion reaction, then coke will convert it into CO2, and its energy is very high. It's around 7,800 kilocalorie per joule. Kg, kilojoule per kg. It's like that. It's heat is. So because of full combustion, coke will be burned fully. At the same time, temperature of regenerator will go very high, and because of this, that catalyst circulation will go down, because at very low circulation rate you will maintain this reactor outlet temperature if full combustion mode is taking place. While if in partial combustion, coke may convert it into CO, and this the heat generation will be less, and in that case catalyst circulation rate may increase. So depending on the condition, but at the same time, if CO is there, then this CO may need to convert it into CO2 in CO incinerator. So this flue gas will in that case will go into CO incinerator. It's a kind of thing. So I will not go into detail about this due to time limitation, but anyway, there could be different type of regenerator section, and in every regenerator section, uh, in the presence of air, catalyst, coke on the spent catalyst will burnt out, and then our active site is again available for reaction, and that regenerator catalyst will flow through this RCSB again into riser. So I will discuss about some of the important parameters in FCC. I mean operating parameter. Generally, we maintain furnace outlet temperature, coil outlet temperature around 220 degrees Celsius. So here, what it is written, this feed is coming from feed surge drum with pump with feed preheat furnace, and it is going into the riser, and the preheat temperature is around 220 degrees Celsius. Okay, and then reactor outlet temperature means temperature at the riser termination device is around 514 degrees Celsius. Pressure given on reactor pressure around 1.4 kg per centimeter square G. Okay, and then this catalyst, after this reaction, we have here, this is a stepping stone. After this reaction, it goes to regenerator through a spent catalyst slide valve, and then uh, in this residence time, as I have explained, it's around 2 seconds. And in regenerator, if it is two-stage regenerators, then the temperature are like this. This is 700 degrees Celsius in regenerator 1, and in regenerator 2 750 degrees Celsius. So you see that the catalyst temperature is going very high due to exothermic reaction in regenerator, while in riser there is a endothermic reaction, that is cracking reaction, and because of this endothermic reaction, reactor outlet temperature will go down up to 500 degrees Celsius. So catalyst is coming from 750 degrees Celsius to rise a bottom, and during this movement catalyst temperature will go down up to 540 degrees Celsius. Okay, now I will ask, based on this pressure, how catalyst is moving from, say, at 1.4 kg per centimeter square gauge pressure of reactor to the regenerator section where pressure is 2 kg. I mean, how catalyst is moving from low pressure region to high pressure region. This you need to answer while our discussion after some, say, for 5 to 10 minutes. Okay. Anyway, now what are the dp which we maintain is around 0.4 kg, zero point 0.5 kg per centimeter square. So this is the only margin in the whole circulation in reactor riser section. Okay. uh, and these are the catalysts I have already discussed. These are the reaction, exothermic, endothermic reaction. Okay, and whatever the products we get, there is a series of distillation column to separate these products. I will not go into detail, but the product we get is depend on the design of the FCC. It can be different, as I explained, that it can be in max. Their LPG production will be very high, and LPG production could be, say, 30 to 35%. Here I have explained that is LCN production is high. So it's not very important for you because it can vary from a large range. Means if it is in max, so this LPG could be 40%. If it is gasoline mode, then this could be 30 to 40%. If it is diesel mode, then this is 34%, like here I have explained. So this is the one of the FCC which you run in diesel mode. Usually nowadays FCC is usually for gasoline and LPG, while hydrocracker is for diesel. So these type of design weight percent is may not be the actual operating range. So if you see that this FCC was designed for 34 weight percent product yield of LCO, while they are operating only of at 15 weight percent, while LCN is 44 weight percent. So you see that the unit was designed for some other thing, and they have just changed catalyst oil ratio and catalyst, and they are operating at very different zone. Anyway, so till now I have discussed about a general FCC, but right now I am discussing about a special type of FCC called RFCCU. RFCC is a special type of FCC. Why? Because in RFCCU feed there is a vacuum residue. Also one component will be VR also, that is called short residue, and because of this the name is RFCCU. Means there is a catalytic cracking reaction taking place in fluidized bed, and in feed there is one component of VR also. Okay, and this we are having a lot of problem. What could be the problem? I will explaining here. Okay, so when we add VR in the FCC feed, its CCR increases. It could be go up to 48%. And apart from this, with VR, there is some metal also come into feed, like vanadium, nickel, basic nitrogen. Apart from this, there will be sulfur, aromatic or asphaltene type of material. So because of these, there are several problem creates. Why? As I explained about the catalyst deactivation, one catalyst deactivation is metal poisoning. Okay, so in if we are processing RFC in RFCC, if you are processing VR, so with VR, vanadium as well as nickel is also coming with feed, and this nickel and vanadium, basically it promote dehydrogenation reaction, and because of this dehydrogenation reaction, more hydrogen, or basically it will form more dry gas, or fuel gas will formation will be high, and because of this it usually limit our wet gas compressor capacity. So I will explain about this. And whenever there is a dehydrogenation reaction, as well as there will be some coke formation also. So because of this VR, dehydrogenation reaction will increase, and these all increase dry gas yield as well as coke yield. And because of this high coke, regenerator temperature will go high, and this will reduce our catalyst circulation rate, and because of this catalyst circulation rate, conversion will reduce. Okay, And apart from this, in between this nickel and vanadium, nickel having 4 times higher activity for dehydrogenation than uh, than this vanadium. And so to avoid this, what we do is we add nickel passivator. So basically nickel passivator, what it does, it react with nickel and it forms some compound which does not promote this dehydrogenation reaction. Okay, now what about vanadium? Vanadium is, apart from promoting this dehydrogenation reaction, they can also destroy the zeolite structure at high temperature. And this is the reason, because of this, we had two stage regeneration in this RFCC unit. Why here it is written RFCC? Why? Because this vanadium at very high temperature react with oxygen from V2O5, and at very high temperature this vanadium pentaoxide react with H2O and form vanadic acid, and vanadic acid can destroy catalyst structure. So to avoid this, what we do is we do two stage regeneration. In first stage regeneration, we do not allow at very high temperature, and at that time hydrogen will be converted into H2O, and flue gas, whatever hydrogen will be converted into H2O will move out to. And then in second stage regeneration, there will be high temperature, but there won't be H2O to react to vanadium uh, pentoxide with H2O to form vanadic acid. So in this way, due to with two stage reaction, we avoid this vanadic acid uh, uh, catalyst destroys. Okay, so here I have explained that two stage regeneration why is required, because these reactions we need to avoid, otherwise it will deactivate the catalyst. And how we can do it? At first stage, uh, we will we will limit this, I mean in the second stage we will limit this H2O, while in first stage we will reduce the temperature, we will not allow at very high temperature. Okay, now this is again another slide which tell about the catalyst poisoning, and this is the summary of the resid processing in RFCC. It tells what are the problem create what these components, like nickel promote dehydrogenation reaction, it will form more dry gas. Okay, similarly sulfur produce high SOx in the product. Basic nitrogen, because it is basic, then it will react with acidic site of zeolite and again it neutralize the catalyst. Aromatics will form more coke. Okay, CCR, high CCR again form more coke, and because of this regenerator temperature will go high, and these all reduce catalyst circulation ratio. So these are the some issue with resid processing. uh, I hope you understand it. Now one very important concept in FCC is that is called heat balance. uh, this is very important. See, heat balance in any unit could be important to know whether our unit are energy efficient or not, but here in FCC heat balance is having much more importance than just checking the energy, because uh, with the heat balance we understand how one variable will affect another variable. So heat balance is key to better understand how different variable interact with one another in FCC unit. And why? Because FCC unit catalyst adjust catalyst circulation in such a way that reactor regenerator heat will remain balanced. So unit will adjust itself in such a way that the heat generated in the regenerator will be consumed in heat of reaction in reactor. So there are several type of heat, during reaction there is a heat of reaction, so this is a heat sink, some heat losses will be there, some. So we what we do is we do a heat balance, and based on heat balance we have some independent process variable and some dependent process variable. Like in FCC, we cannot regulate all the temperature by ourselves. Means if in our hand reactor temperature is there, feed preheat temperature is there, catalyst activity is there, and recycle rate is there. If I am controlling these are independent variables, then these these variables will be dependent, these variable will change based on heat balance. It will change in such a way that the unit will remain in heat balance, means whatever the heat is generating will be consumed. So because of this, heat balance in FCC is very important, and a better understanding of it is required. So I've just introduced about it. I will not go into detail of heat balance. I will share this slide. If you go through this, you might understand. And based on this, I have explained how this reactor temperature. If you increase reactor temperature, how these other process variables will change. So I hope you guys have got some understanding of FCC. FCC is a very vast topic. I cannot explain in 1 hour. I am working for say 7 to 8 years in FCC, and I have tried to summarize the basic of FCC in this lecture. So I hope you have enjoyed the lecture. I am going to stop this lecture. Thank you.